Ropey time. We're on 2D composite functions. We've got two different types of notation. If you're like me, you prefer the notation here on the right, but certainly that notation on the left is also acceptable. The important thing to remember is that we do these kind of from right to left. In both of these examples, we're doing the function g first, and then whatever answer we get, we're going to put into f. By the way, there are like a lot of other notations for composite functions out there. They're used different. By the way, there are a lot of different notations out there for composites of functions. By the way, there's a lot of different notations out there for compositions of functions. They're all used in kind of their own different branch of mathematics where the notation is just easier to use than one of the others. You're unlikely to see anything besides either of these two until you're well into university mathematics. So these two will serve you well for a long time. Now, down below, we talk about the domain of a composite of two functions. It kind of depends on what the original two are. You need to make sure that the function that you started with is still satisfied by the final composition. So in this case, we have two very simple functions, x squared and the square root of x. X squared has a domain of all real numbers, whereas the square root of x is only defined for x greater than or equal to 0. If we were to put these two together, well, the square root of x squared is just going to be x. And I might look at that and say, oh, well, x is defined for all real numbers. So that's the domain of the composite of the two functions. But that's not true. Because my first function, g of x, square root of x, that was only defined for values that were greater than or equal to 0. So there's no way that I can be putting in values that are less than 0 into this composite when I think of it as being the child, if you will, of f and g. Of course, if I'm looking at just the regular function, y equals x, yeah, that's defined for all real numbers. This is not the regular old function, y equals x. This is a composite of x squared and the square root of x. So here in general, f of g of x is not going to be equal to g of f of x. So I don't want you to ever think that those two are the same. It'll be very rare that they are. Let's just go through these really quickly. Let's find f of g. To find f of g, we're going to put g into f. In other words, it's x plus 1 over x minus 1 plus 3, all divided by x plus 1 over x minus 1 plus 2. This is exciting. This is a whole lot of fractions. Boy, you better be loving this right now. We're going to combine the denominators here. So this is going to be plus 3 times x minus 1 all over x minus 1 all over x plus 1 plus 2 times x minus 1 all over x minus 1. Whenever I see this, where the denominator is the same for both of these, just cancel it out. That should be obvious. If you think about it, you're taking a fraction divided by another fraction. So you know you would have to multiply by the reciprocal of this. The end result is going to be this divided by that. But it's quicker if you don't write it out as multiplying by reciprocal, much, much faster if you just know, oh, they're both being divided by the same value, just cross them both out. Putting these together, we're going to get x plus 3x is going to be 4x. 1 but minus 3 is going to be minus 2. On the bottom, that's going to be 3x. And then 1 but minus 2 is going to be minus 1. This cannot be simplified at all. That's what f of g of x is. You might, of course, be asking yourself now, is it possible that g could output something that was negative 2? What's the domain of this composite function? Well, I mean, because clearly g puts out x cannot be equal to f can't take negative 1/3. If it was, I'd be dividing by 0 here. It is possible for g to put out negative 2. And then I also need to go back and but that's only going to happen my original function, the one that we've already covered that. In fact, you'll never really have to check for that. If you're interested, you can do the work for letter b. Letter b comes out to be just the function 2x plus 5. It looks linear, but is it true that x cannot be equal to negative 2? Is that a problem? Negative 2. No, because if I put negative 2 into this composite function, so they're clearly not the same. If you want to think about letter c, and g has no problem with negative 2. G only has a problem with x equal to 1. Here's another fun one. We're going to compose f and g here. F is square root of 1 minus x, so I'm going to put x squared into that. So f of g is going to be the square root of 1 minus x squared. I know for the domain that I need 1 minus x squared to be greater than or equal to 0, since it's a square root function. Solving that tells me that, well, how would I approach this? You might be tempted to move that over, and then you can probably tell from here that you're going to have to take square roots, and plus or minus 1 are going to be important values for you, but it might not be obvious. Is it just those numbers? Is it in between those numbers? Is it outside of those numbers? So instead of doing it that way, what I recommend is factoring. And drawing a sign diagram. Again, that's officially from Chapter 2, Section F, but I think you should have already watched it by now. My two important values here will be -1 and +1. -1, of course, from the right factor, and +1 from the left. Using a test value, in between them would be 0. If x was equal to 0, I will have 1 times 1, which is a positive number. If x was bigger than 1, say 2, I will have a negative times a positive, which is a negative. And likewise, if x is less than -1, I'll also have a negative value. So where is this greater than or equal to 0? Well, only in between and including -1 and +1. Thinking about the range now, again, let's imagine what happens at these extremes. When x is equal to -1, the y value is going to be equal to 0. And when x is equal to +1, the y value is going to be equal to 0 again. We can start to sketch out what this might look like. When x is any number in between -1 and 1, we're going to have a positive number come out. It's the square root of a positive number. I know that it's not plus or minus. If it was plus or minus, by the way, then that would not be a function, and we are kind of assuming that it is. It's kind of implicitly assumed in the question. I'll talk more about that in a second. The maximum place, like the highest positive value we can have, is going to happen kind of in between these two extremes. So when x is equal to 0, we're going to get the square root of, well, just 1, which is 1. And basically the shape we're going to get is this. And if you test out other x values, you're going to see that this has to be the shape that we get. If we had included the plus or minus, then I would have a minus down here. And it kind of looks like a circle, and actually it is another circle. This is going to look really similar to a previous circle question we saw. Here, if I have y is equal to the square root of 1 minus x squared, that means that I could write y squared minus x squared equals 1. That is a circle whose center is at the origin and whose radius is 1. And that's exactly what I've drawn, although that's not a particularly pretty picture there. Okay, here's another spin on this topic. Letter A, I mean, hopefully this is obvious to you. If we know in advance that two lines are the exact same, if ax plus b is equal to cx plus d for all values for x, then obviously their slopes need to be the same and their y-intercepts need to be the same. I can't imagine how this could be untrue, but we're going to algebraically show that now. And they are kind of nudging us along on saying that, you know, if it's true for all x by assumption, then that means it has to be true for x equals 0 and x equals 1. So let's see what happens when x is equal to 0. Well, then I'm going to have, oh, if x is equal to 0, then b has to be equal to d. And if x is equal to 1, then I know that a plus b has to equal c plus, I could write d, but I already know that d is the same as b, which means that I could cancel the b's, and of course, a is equal to c. Moving on to letter B, a little bit different. We have two functions here, f and g, and I want to deduce these values for a and b. But even if I didn't have the answers ahead of time, anytime that I am being asked to figure out two different values, I know I need to do a system of equations. So here's what that system might look like. Now I know that the composite, this is going to be important here, f of g of x is just equal to x. So let's figure out what the composite f of g of x is. F of g is going to be if I put ax plus b into f. And that needs to be equal to x. And we can see that this is going to give me a little equation that I can simplify. So now I know that 2ax plus 2b plus 3 is equal to x. And now from here, if we just think about this in the same light as we did letter A, we can just check, well, we know it's true for all x. So what happens when x is equal to 0? When x is equal to 0, I know that 2b plus 3 is equal to 0. And yeah, that's going to immediately give me that b is equal to negative 3 halves. And if I put in x equal 1, I'm going to get a equal 1 half. No problem. Letter C, is the result in B true? In other words, are these still the values for A and B if instead of doing f of g of x, we did g of f of x? Incidentally, yes, you do still get the same A and B values. You can check that on your own. Now, if you're like me, you're wondering at this point, is there something special about 2x plus 3? Is there some particular reason that in this case, g of f of x and f of g of x both being equal to x give me the same a and b value? That was a lot of words, but like that was not expected. I certainly did not expect it to be the same in both cases. Composites are generally not the same, but in this case, forcing them to be the same force this second function to be the same thing. So you could generalize this even further. If I have f of x being ax plus b and g of x being cx plus d, I could work out both of their composite functions as I did here, and I'm setting them both equal to x. That's by assumption. And I want to show that both of these will give me the exact same values for either c and d or a and b. I'll do them for c and d, but that was just an arbitrary choice. Using the same rules as before, here I know that if x is equal to 0, then I'm going to get AD plus B is equal to 0. And from here, I know that when x is equal to 0, I'll have BC plus D is equal to 0. I might also check then what happens when x is equal to 1. Well, when x is equal to 1, I'm going to have AC plus AD plus B is equal to 1, and AC plus BC plus D is equal to 1. Well, let's work with these. Since I want to find out C and D, and remember in the previous example, we found out what A and B were in terms of numbers, and the only numbers are really coming from over here. So I'm going to do a similar thing here, which is I'm going to say, for example, this tells me that D has to be equal to negative B over A. And that's putting this value in terms of the other function. And I can tell from the other one that D has to also be equal to negative BC, but the problem is that C is part of the same function that D came from. If, however, I could show that these two were equal to each other, then I'd be set, and that's exactly what I'm going to do. Let's now set and that's exactly what I'm going to do. I'm actually going to use this substitution, D equals negative B over A, in this line. That's going to give me that AC plus A times negative B over A, or just minus B, but plus B is equal to 1. Erase that for just a second. And then from there, I can then deduce that AC is equal to 1, or C is equal to 1 over A. So I've got I've got this, and I've got that. Working with the other set, I had previously worked out that d was equal to negative b over c. But you know what? If c is equal to 1 over a, then that's negative b over a. Oh, that's exactly what I wanted it to be. And then from there, it's just a matter of substitution to show that c is also equal to 1 over a. So I don't know. That was fun for me. Maybe not for you, but I like to generalize things. No. So that was fun for me. Hopefully it was fun for you. I really enjoyed generalizing problems when I can. It helps me know that things aren't just special cases. Special cases sometimes are interesting, but most of the time I find them kind of boring. I'm much more interested in really understanding how things operate and why, rather than just being mystified like, oh, what a cool function 2x plus 3 must be. And so that's kind of an approach of inquiry that I want you to really embrace for the remainder of this course. Having an open mind and really experimenting with abstract algebra rather than working with concrete numbers is something we're going to have to get used to if we want to be successful here. So I hope this was worth your while. Catch you later.